Okay. All right. So good morning to people who've got up this early. So I'm going to talk about, I'll start at the beginning and talk about the way Bitcoin is organized and why it is organized the way it is and how that's evolved over time and how we can add new features to Bitcoin and how that's evolving. So I think basically the outline is that we need most network protocols are based on layers, and if you think about Bitcoin as the base layer, it's kind of the TCP/IP, and in networking terms, there are multiple protocols optimized for different use cases based on IP, so voice over IP, web traffic, email traffic, IM traffic. So they have different properties, they make different trade-offs, but they're all based on a reliable core protocol. And in the TCP/IP case, the basic IP protocol hasn't changed a lot in probably 30 or 40 years. And so Bitcoin is intended to be the sort of reliable, dependable base layer and the security anchor for a lot of layer 2 protocols to come. So at present, already probably 3 or 4 different variants of layer 2s. And I'm going to talk about some more layer 2s optimized for different use cases that can be built on top of Bitcoin. So quick recap of what interesting properties does Bitcoin have in terms of why we find it interesting and how it introduced the blockchain concept to the world. So one of the things is that monetarily it's deterministic. We know how many coins there will be approximately at any given time with the mining protocol and a very defined supply. So there's no political committee or coin management group that's deciding how many coins. That's mathematically defined from when it was released in early 2009. So I think that's one important property. Another one obviously is security first. That it's permissionless. So that's one key thing about the internet, that it is permissionless. Any developer can download software, get hold of a compiler, and start writing applications. So that's the way it is with Bitcoin. And that's quite different to previous electronic financial systems. So needing an API from a bank or a merchant integration from a credit card merchant provider was a quite permission type of thing, whereas Bitcoin is very permissionless. You can download some software, receive some Bitcoins, write some applications on top of Bitcoin. One key important part about the base layer is that it should be final. So when you make a transaction, the transaction should be finished and done. So because of the way Bitcoin mining works, it's not that instant. It might take 10 minutes. It might take occasionally up to an hour to get one confirmation, but over time it becomes increasingly final. And that's important because all of the higher level protocols depend on that security property. So the layers above Bitcoin depend on the base layer for their security ultimately. So I'm going to talk about how Bitcoin is organized. So the original source code release for Bitcoin was kind of monolithic. It had components within it, but the source wasn't that well modularized. And there's been a lot of work on Bitcoin over the years since 2009 from hundreds of open source developers working on the protocol, and including a lot of modularity improvements, splitting things out into separate modules, introducing features that help make layers secure, and optimization of different parts of the system. So there are broadly 2 areas of the code. One is the so-called consensus layer. So this is the area where you would run into difficulty and risk an accidental chain fork if 2 implementations or 2 different versions of the same implementation differed in even the slightest way. And so over time, that's been increasingly modularized because it's a particular risk point that a lot of attention has to be paid to if there are changes. So that's the lib consensus module, which is becoming a library so that other implementations can use it. And also the way that Bitcoin changes have been introduced over the years has always been with an eye to backwards compatibility. And so changes are introduced into Bitcoin via a so-called soft fork. So it just means that an old wallet or an old full node can still function in the network. And indeed, you can just about run today the original version of Bitcoin, and it will eventually catch up with the network. It will just be very slow because there are many optimizations that happened in the meantime. They're also possible to add new algorithms and features. So Bitcoin is organized as the scripting system of Bitcoin is organized as a kind of opcode-based stack machine or stack language. And it's possible to add new opcodes to support new things. So we'll talk about that soon. It's important as well that a system that you rely on be decentralized, because centralized things are at risk of shutting down. We should remember, for example, in peer-to-peer file sharing, that Napster ended up being shut down and disbanded, where decentralized things like BitTorrent kept running. And there are many examples of that. So there were previous electronic cache systems, and one of the speakers here today is David Chaum, who actually invented some of the original electronic cache protocols and operated a company that had a more centralized architecture. So Bitcoin differs from the previous generation electronic cache systems in being more decentralized, and so better at surviving the longevity of a given company. It's more of a fabric that anybody can use. And better at providing finality, because there's nobody in control that you can ask to undo a transaction or change something about the system. And that's counterintuitive, but is a sort of side effect of lots of cross-checks and balances in the system. So there are a large number of independent developers who are cross-checking each other's work, but whatever software the developers write, it doesn't have any force in the network unless the economic users choose to run it. So that's kind of one economic check that people who are running full nodes, just power users or businesses like exchanges and payment processors, will choose to upgrade or not. And the upgrades are typically, so far almost always been opt-in unless there's a bug to fix, so that you can use a new feature if you want to. You can upgrade if you want to. If you don't upgrade, you lose some incremental security assurance, but it'll still be compatible. So as an example of a network of an upgrade that doesn't affect compatibility, there's a part of the Bitcoin protocol where you plug in a new node and it syncs, so it fetches the full history of transactions since 2009. And as you can imagine, that's quite a lot of data. It's on the order of 250 gigabytes today. It's still fairly compact compared to some other blockchains because it's optimized for size and keeps application state outside of the blockchain by design. And that system has been overhauled and rewritten 4 times, each time becoming about 10 times faster than the previous time. There isn't that much left to optimize. It won't get 10 times faster again. So that's where that's got to. But it's an illustration of the kind of change process. But there are other areas of the network protocol that are evolving. So this is recent work by Greg Maxwell, Peter Wohl, and Gleb Nomenko to use some set reconciliation for lower bandwidth ways to pass transactions between nodes. So Bitcoin is a flood network. When you make a transaction, it gets broadcast through the network. And so there tends to be redundancy in the networking. So set reconciliation can reduce the sort of bandwidth waste that arises from sending the same transactions across the same link twice. And because of that, you can increase the connectivity, which sort of improves the resilience of the network to different types of network attack, at the same time as lowering bandwidth. So this is something that may happen in the midterm future, maybe into next year or something. There have been a number of bits of library source code released, and more recently a BIP for this one. Another example of something that's happening at the moment is Schnorr signatures. So it's just a smaller signature. It's more compact, particularly for multi-signatures, so signatures involving multiple parties. It has advantages of a Bitcoin transaction is composed of coins, and sometimes there are multiple coins that go into a transaction to make up the amount. And so you can combine a signature across all of those inputs if they're from the same person. And it also has some privacy advantages. So with Bitcoin today, it's sometimes possible to distinguish which type of wallet created them. So you can maybe distinguish a Lightning channel setup from a multi-sig wallet from a single-sig wallet. And with Schnorr signatures, in particular Taproot, some of that fingerprinting goes away. And it actually improves scalability as well, because all the blockchain sees is the default single signature. And behind that, in the case of an exception, more details provided. Another interesting thing about introducing Schnorr signatures is it shows that Bitcoin has the capability to add a new signature algorithm, which may become important in some decades to come, if and when powerful quantum computers finally created, which is a bit of an open question at the moment. Tends to be waves of sort of excitement about quantum computing, but to date they've been very far short of being a threat to conventional digital signature cryptography that Bitcoin uses. So now onto the layering. So there are various layers. Lightning was the first, one of the most well-known and very actively developed at the moment. There are many startups working on this, including startups working on hardware wallets, working on payment integration, merchant adoption, so they pay out in US dollars, euros, etc., and the user can pay in Lightning. It has, it does rely on the Bitcoin main chain for security, because if somebody tries to claim more money than they should, you can contest it, and so you can kind of use the main chain as the security assurance. And normally, you can operate entirely within the Lightning channel. So it's just another way to store Bitcoins that enables them to be moved off-chain. And if something goes wrong, you can go on-chain to claim the Bitcoins that you're due. So there is a slight shift in the security model because you have to notice that something was going wrong or delegate to somebody else to notice that something's going wrong. So that's what the reactive security model is about. But the payoff is you get a much more scalable form of payment, because very few of the transactions have to go on the chain, and the chain is broadcast and expensive, like it uses a lot of storage. So as well as being about 250 gigabytes to download, there are estimated to be around 100,000 nodes around the world, so it's a lot of bandwidth ultimately that's broadcast. If we expect Bitcoin to be adopted by many more millions of users, then we need more scalable ways to use it. And Lightning is a great way to benefit from the Bitcoin base layer security and get more scalability. It's also faster. The transactions are immediately final, sub-second, and typically cheaper as well. And there are more things happening with Lightning. So there's a second version that people are working on now called L2, which adds splice in and splice out, which is basically a way to be more backwards and forwards compatible with non-Lightning wallets, so on-chain wallets. And personally, I would expect that mobile phone-based Bitcoin wallets would migrate to Lightning midterm, because it's just a better experience and can cope with the types of amounts that you would expect people to store and use on a mobile wallet. So another kind of layer 2 is a sidechain. So it's a way to have another chain that's kind of like an altcoin, but without any native coin. So the only coins in it are Bitcoins that go into it, or potentially some kind of issued asset. So some chains introduce user-defined assets like a Tether US dollar coin or security token coins. Then there's a way to move money between the sidechain and the main chain. So you can peg Bitcoins between the main Bitcoin chain and the sidechain, and then use the new features that you get from the sidechain. And at a later time, so a user who then holds the Bitcoin, doesn't have to be the same user, can peg it back out to the main chain. So there's 3 examples here. One, they're variant types. One is a federated chain that's liquid. Merge mining is another way where Bitcoin miners can mine both chains. And another one is drive chain. And there are hybrids that do a bit of merge mining and a bit of federated. So Rootstock has that, which is another sidechain. So I'm going to describe briefly the liquid sidechain, which is a product by Blockstream. It's for exchange traders. It's federated, so the blocks are signed and not mined. And they're signed by a federation. So actually, 2/3 of the members have to sign for a block to be valid. And they do so with rack mount servers with HSMs in them that sit in their data center alongside their exchange equipment. So it is a trade-off, but for exchange traders, it's a step up from single exchange custody. And the liquid sidechain introduces a number of interesting features, probably most famous being confidential transactions, which adds a certain degree of privacy, hides the values of the transactions and even the types of the transactions, because that can be Bitcoin as well as Tether and security tokens, etc. It has a built-in atomic swap and some smart contract extensions. So the Liquid ecosystem has a lot of the building blocks you would expect: wallets, hardware wallet support coming, 2 different wallets provided by Blockstream, third-party wallet by RenRenBit. There are 35 exchanges involved in the network, 2 in Korea, Coin1 and GoPax. There's a block explorer. And so if you're interested to try out confidential transactions, you can download the Green mobile wallet application on Android or iOS and try it out. You can put Bitcoin in and make user-to-user payments with it. So another older kind of layer 2 that hasn't actually been implemented, but it's an interesting idea. So it's just to show that there are different ways and a lot of scope to add more types of layer 2 to Bitcoin, is a so-called private chain. So it's basically the idea that you could have a chain which is just operated by a set of servers as long as you had the ability to unilaterally withdraw from it. So let's say there's a single server over here, and it's signing blocks, and you send it transactions, and it puts them in blocks, and it signs them and moves them on to the next block. You can run a full node. You can look at the transactions and blocks that it's relaying. And if it does something you don't like it won't process your transaction, or it tries to rewrite history, you can just take your coins out and take them to the host chain. So the host chain could be a side chain, and that was the original idea, but it could also be the Bitcoin main chain if the Bitcoin main chain had a couple of other new opcodes to support this unilateral withdrawal concept. So unilateral withdrawal just means that if you want to take your coins out, you just assert that these are your coins. You show a previous block where you owned them in the sidechain, and then they're yours unless somebody contests it. So other users of the sidechain or sidechain operator can, because it's a single server kind of sidechain or a federated server, they can contest it by proving that there was a later block where you transferred the coin to somebody else, and that would preclude you from requesting that it be sent out. And this kind of sidechain is basically, it would typically be based on the UTXO model, so it's just another Bitcoin-like chain, and it could have different parameters. It could be bigger, it could be a little bit more centralized, it could be faster. So the layer 2 is still evolving. So Ruben Sumson, who is Korean, somebody who lives in Korea and works on Bitcoin, recently proposed something called a state chain, which is a different configuration and somewhat similar to the private chain, but buildable with today's Bitcoin. So you don't need any new features to do this one. It has a unilateral withdrawal using some Lightning-like features. It has a trade-off that you can't split the coins apart. So you put half a Bitcoin in, it has to transfer around at that denomination. So you have to kind of make a change. If you want to make a payment of a different amount, you have to get paid back with a smaller coin. Whereas with the private chain, they're varying sized coins, and they can make change on the side chain. So it adds a possibility of blind signatures. There is a bit of trust in the federation to not collude with users, but other than that, as long as the threshold of the co-signers of the sidechain or state chain are honest, then they won't take your coins. And if something goes wrong with the state chain, you can take your coins out. So it's an interesting direction. It's just an idea stage. It hasn't been implemented. Another older one, I think I first proposed this one in 2014, is extension blocks. So it's a bit like a sidechain, except that you're expecting that the main Bitcoin chain should validate that the blocks on the sidechain, the blocks on the extension block are valid. And that's good in elevating the security of the extension block to the same as Bitcoin, but it has a number of side effects. So it does prevent coins. It prevents problems on the main chain, so if you opt into the extension block, you're the one taking the risk. But it does import the potential for bugs, particularly in non-determinism, so unpredictable behavior in the extension block into Bitcoin, which could be quite bad as a side effect. But in principle, we could fix the determinism using a deterministic execution, so you can verify the extension block logic in an interpreted abstract virtual machine that is deterministic. And an example of that is simplicity, which I'll talk about in a minute. Generally, what makes it unattractive, though, still, is that it's effectively a block size increase. So if you were going to increase the block size, you could as easily do that in the main Bitcoin chain, unless there was some reason to make a kind of compartment to try a feature that not everybody wanted to use, so the kind of opt-in module. So another idea proposed by Gregory Maxwell is to use the zero-knowledge proofs of execution, so a more recent cryptographic invention called snarks, and bullet proofs are another variant of that more recently. So there you get some very new and novel mathematical concept of having proof that a program has run on some data, and that proof can be relatively small, like a digital signature, and it proves that a program was run on a data that you haven't seen. You've just seen the hash of the data, and a new hash of the sort of new block has been created, and you can sort of verify that all the rules were followed in the transactions on this sidechain. It's an enormous computation for a snark or a bulletproof, so there remain significant scalability challenges with it. We need much, much faster snarks or bulletproofs, and snarks themselves introduce some novel security risks because they're very new in experimental cryptography. The bulletproofs use conventional cryptography but are not quite as compact. But it's an area of active research, so at a point in which this kind of cryptography becomes efficient enough, it could be pretty interesting. So I would expect there will be more layer 2 things in the future, and that's good because Bitcoin can benefit from different layer 2s offering different advantages like better privacy or scalability in a different way to Lightning. So I'm going to finish up with a last topic, which is a bit of a longer topic, which is a general self-extensibility mechanism for Bitcoin and Bitcoin-like blockchains, so Liquid being a Bitcoin-like blockchain. So it is a programming language, quite low-level programming language, kind of like assembly level, but with formal semantics. And those formal semantics are designed to allow you to prove things about programs, to prove they're correct or prove they always behave in the way you expect they behave. So, and because it's low level, there's a need to make a library of functions for higher level things so that the programs don't get too big. So a jet is a kind of collection of library functions that have been pre-implemented and validated. This is all work by Russell O'Connor, originally dated back to 2012, and he's been working at Blockstream on this for a few years now, and we've made some releases on it. We're initially proposing to roll it out in Liquid as a way to try it out, and if that is interesting to people, we might eventually propose it for Bitcoin and see what people think about it. So it's an interpreted language. There is an abstract machine that executes it. Some details about the machine. The simplicity, there are 3 simplicity interpreters. The one written in Coq, which is a general purpose proof assistant, is formally verified to execute simplicity programs correctly. So it's not often you get an interpreter that you have a proof will always correctly execute all programs written in its interpreted language. And we also have a C implementation, and there's a path to proving the formal correctness of the simplicity program, the C implementation, by using verifiable C and proving it's equivalent to the COC implementation. So simplicity is a mathematical type of language, so it sounds difficult to think about how you would prove things, but it's proven because it's very low level and mathematical, so there are just 2 pages of it. These 2 pages are the full definition, so it's done using kind of bit level operators and data structure concatenation and so forth. So what could you do if you had simplicity available in Bitcoin today? So we've talked about a couple of things here. One of them was Schnorr signatures. You could implement Schnorr signatures as a simplicity program without requiring a soft fork. And people could try it out. You can make different versions of it. And I mentioned Lightning L2, which is the second version of Lightning. It needs another soft fork for something called no input. With simplicity, you wouldn't need that. You could just implement it as is. And it's also just a more general programming model. So you can write all kinds of things. So a partially matched swap transaction, non-interactive limit orders, vaults are quite interesting. So it's a way for you to store Bitcoins such that you need notice to remove them from storage. So that improves the security because you can have Bitcoin stored, send a special transaction to the blockchain to notify the blockchain that you're about to take some coins out of the vault. And you have a week in which to cancel it. And during that week, other people who you can delegate to are able to cancel withdraw transactions. So that protects you from various kinds of theft because third parties can notice your coins are moving, or you can notice they're moving when you weren't intending them to move, and cancel it. And you can do all of these things with formal provability about constraints and invariants about the program. So when is this happening? So we did a developer preview of Simplicity last month, and we're going to do a developer release with the jets added to it. So there's a library of common functions so that the programs are smaller. And we're targeting to make that available in Liquid itself next year. And it's Bitcoin compatible, so it may eventually become available in Bitcoin and become a general extensibility method for Bitcoin. So I think that's interesting in making Bitcoin's sort of rate of change slower in a sense, or at least it's sort of non-backwards, or it's sort of adding major new features process more automated. So, and another interesting thing is if you add, let's say, a Schnorr signature using Simplicity, you could send a special opcode, which a special UTXO, which held the Simplicity implementation of a Schnorr signature. And you could later make a soft fork with a faster C implementation. And that would mean that software that hadn't upgraded would still have a full understanding. It wouldn't be a soft fork. It would just run slightly slower. So, and then you could opt to upgrade to the C implementation of the same feature, which would be formally proven to be equivalent. So that's it. So thank you.
Thank you. Do you want to take any questions very quickly? Anybody's any questions? Anything? Calling once, twice. Okay. Thanks very much, Adam. Thank you very much. All right.